Welcome to this video on sample proportions. By the end of this video, you should be able to calculate the mean and standard deviation of a sampling distribution of a sample proportion and interpret the standard deviation. You should also be able to determine if the sampling distribution of a sample proportion is approximately normal, and if appropriate, use the normal distribution to calculate probabilities involving a sample proportion. So today's scenario is, what is the proportion of orange Reese's Pieces? So if we take a sample of Reese's Pieces, what proportion of the candies will be orange? So we're going to make a scenario of, suppose there's a very large bag of Reese's Pieces and it has 1,000 pieces in it. The manufacturer says exactly 40% of the candies are orange. If we select a sample of 50 pieces, how many will be orange? And we're going to assign the random variable x to be the number of orange candies in the sample. All right, so what type of probability does this distribution have? So we defined our random variable x to be the number of orange candies in the sample. So that makes me think back to our binomial and our geometric distribution. So let's take a look to see if this works. Let's check our bits or bins. That would determine what we've got going on here. So what type, do we have a binary? So we have a success will be an orange candy, and a failure will be not orange. So we have binary, we're good there. Independence, we have no replacement, which we talked about before. That might mean this is not independent. However, our sample size of 50 is less than or equal to 1/10 of our population. And if you remember, that's what we called the 10% rule. So as long as that's true, they're independent. So we're okay there. So we have independence. Our sample size is 50. Now, we have a set number that makes it binomial if it's going to work, and so we're good there. And then, do we have the same probability of success each time? Well, the company claims it is 40% orange, and we said we could go ahead with the no replacement because of the 10% rule, so we're okay there. So we've got a binomial setting here. So what I'm going to do is I'm going to show you this applet, and we're going to draw a sample of 50 Reese's Pieces 5 times. So here's the applet. It's the Rossmann Chance Reese's applet. The probability of orange, the company told us, was 0.4, so I'm going to change that to 0.4. We want to draw 50 pieces of candy, and it's going to tell us the number of orange below. So we're going to draw one sample. It's going to take a second, so that we got 16 candies this time. I'm going to draw another sample. I got 20 candies this time. For our third sample, $20 candies again. Our fourth sample, got 18. And now our fifth sample. Nine. Okay. All right, so these are our samples. Let me show you the sampling distribution that we created when we were in class. All right, so here's our sampling distribution of the random variable x. That's not an x bar because these are not means. They are the random variable x numbers, which we defined as the number of candies in the orange sample. Okay, so make sure you get a copy of this. And remember, a single dot, one single dot represents one sample of 50 Reese's and the number of orange. Okay, you always have to know what your dots are representing. All right, so we know what each dot represents. Now let's talk about the mean and the standard deviation. This has to throw back a little bit to our random variable x, so that's from Unit 5 and 6, so we got to go back there. So what is the mean and the standard deviation? Well, let me give you some formulas here. Your mean of the random variable x equals your sample size times your proportion. Okay, so to find the mean of x in this particular case, our sample size was 50 and we had a proportion of 0.4, so we had a mean of 20. Okay, let me also remind you of the standard deviation. It was the square root of n times p times 1 minus p. Remember, these formulas are on your formula sheet. So to find the standard deviation, we're going to take our sample size times the probability of success times the probability of failure, and we're going to get 3.46. All right, so what is the approximate shape of the sampling distribution for x? Explain and sketch it below. Well, another thing that we talked about previously was something called large counts. If we had at least 10 successes and 10 failures, we could say it's approximately normal. Even though maybe looking at this, we're not seeing it yet, but we can check it. So if we take 50 times 0.4, and I do want you to show you the work for this. We just did that. That was 20. Well, that is greater than or equal to 10, so our large count works there. So remember, we want to compare it to 10, and then we want to do failure. So a sample size of 50 times the probability of a failure of 0.6 gave us 30, and that's greater than or equal to 10. So we have large counts, so that means our distribution will be approximately normal with a mean of 20 and a standard deviation of 3.46. So we would draw it like that. Mean of 20 and a standard deviation of 3.46. Okay, so all the stuff we got to bring back, even though we talked about it last semester. So the official large counts is n times p has to be greater than or equal to 10, and n times 1 minus p also has to be greater than or equal to 10, and that means it's approximately normal, if that is true. All right, let's keep moving. All right, so on the back, instead of finding the number of candies that are orange, we're going to talk about the proportion of candies that are orange. So we're going to use our samples from number 2 and turn each of the numbers into a p-hat. Okay, and to do that, you are going to take each of the values and divide them by 50 to get our p-hat. All right, so here is our dot plot where I have converted all of the numbers from the front into their percentages. You take each value and you divide it by 50. So now this one, we would title, it's the sampling distribution of p-hat, because that's what it's representing. So we want to make sure we've got that on there. Each one of these dots represents a statistic proportion from our sample. So any dot you choose, that's going to be one sample of 50 Reese's and the proportion of orange. Okay, so one sample of 50 Reese's and the proportion of orange. Okay, so now I want to find the new mean and standard deviation. So when you're taking samples, if we're finding a mean, we did the n times the p, and so with our sample, you divide by the sample size. So what happens is the sample size, the n cancels out. So the mean of your p hat is going to be equal to your population proportion. That's what we were saying before. We already knew that. That's the unbiased estimator that we've been talking about. So if we want to find the mean of our p hat, well, it's going to be the same as our population proportion, which the company is claiming to be 0.4. Okay, so now to find our standard deviation of p hat, we're not talking about random variable x, we're talking about the p hat. So if you think about it, that we had n times p times 1 minus p, okay, and then you've got to divide it by its sample size. Okay, but what happens is this is really n squared through some math, and so one of the n's, the top n is going to cancel out. So we're going to have, for our final, p times 1 minus p divided by n. So this is the formula that we're going to use, and this is the formula that we're going to use. Okay, it's kind of, all right, so let's see. We've got the standard deviation of p hat is going to equal the square root of our success times our failure divided by our sample size, and we should get 0.069. Okay, so now we have our mean and our standard deviation, and we want to approximate the shape. So when we want to approximate the shape, what we're really wanting to do is look at our large counts. Okay, so that's where we have to take n times p. So our n is 50, our p of success is 0.4, and we actually did this on the front, and because we're doing the same thing, we're going to get the same answers. 20 is greater than or equal to 10, so we're okay here. And we have to do n times 1 minus p, which is 0.6, and we'll get 30, which is greater than or equal to 10. So our large counts are good. So we will have a normal distribution. What that means is because these are both greater than 10, we have a normal distribution with a mean of 0.4 and a standard deviation of 0.069. Okay. Now, we know that the bag of Reese's Pieces contains exactly 40% that are orange. If we select a random sample of 50 candies, what is the probability that the sample proportion will be 50% or greater? Because this is normal, we can do a z-score. And so the information we're looking for, so if we look at our normal curve, we're at 0.4, and we want to know the probability of being at 0.5 or 50%. Or greater. So I want to know that piece of information. Okay, so let's run our z-score. So z equals, the score of interest was 0.5 minus the mean, divided by the standard deviation, which is going to equal a z-score of 1.45, which we're going to look up on our table A to find the area. And when I looked it up, I got an area of 0.9265. But remember, when you look them up, it's talking about the area below, which is all of this. That's not what we're looking for. So we need to do 1 minus, and we'll get 0.0735. So there is about a 7.4% chance of getting greater than 50% orange. All right. Let's go ahead and summarize this down for you. Here's 3 things that I want to be sure that you're able to take away from today's lesson, because it was a lot, is I want to make sure that you know how to find the mean and standard deviation for your proportion. Okay, so to find the mean of p hat, it's just going to be equal to the population proportion. Okay, and to find the standard deviation of p hat, you're going to take the square root of p times 1 minus p, success times failure, divided by the sample size. You can only do this, I'm going to put this in red because I want to make sure you remember that, only if the 10% condition is met. These are assuming normality, so that's why you have to make sure that that is done. Okay, your distribution is approximately normal. Remember, we don't want to be very definitive unless we can prove it. Approximately normal if your large counts are true. Okay. And to find your large counts, remember you take n times p has to be greater than or equal to 10. And n times 1 minus p must also be greater than or equal to 10. Otherwise, your distribution is not approximately normal. Okay. Then if we want to start talking the probability of an event happening, so if the sampling distribution of your statistic, which in this case is p hat, is approximately normal, then you can find the probabilities using a z-score. Okay, and so you'll take your statistic minus your parameter and divide it by the standard deviation of the statistic, of the sample. Okay, then you'll use your table, get your z-score, and you'll get your table A out and look up the probabilities. All right, so this is a lot there, and I want to make sure that you can do. Try these on your own and then come back and check your answers. All right, so here's your answers. I'll move this up in just a second. Your sampling distribution of p hat will be the same as the population, which is 0.08. All right, and then we calculated the standard deviation, checked the 10% condition, interpreted the standard deviation here, checked my large counts. Here's my work for finding the z-scores within 2 percentage points of 0.08. So there's a 0.9736 probability of being in this area. And then if the sample size were 9,000 rather than 1,000, what would happen? The distribution would remain approximately normal, but the standard deviation would decrease by 1/3 once you start taking the square root here. And then the value of the mean stays the same. Hopefully that was helpful. Let me know if you have any questions. See you in class.